Section 3.1, Part 2, Compound Interest. One important application of exponential functions is calculating compound interest. And this is basically any situation where interest is paid on an initial investment. So our model here is going to be doing very simple interest in that we begin with a certain amount of money, and then we just let it sit in an account that pays a certain interest rate on it. And it just grows and grows over time. Now, it's important to understand the setup and the letters to make sure you put the right numbers in the right place for this model. Now, first off, A is the amount of money in the account at any time t. So as a function, t is going to be kind of like the input, for the most part, like what time we're looking at, and A would tell you how much money is in the account. So we call that the balance. The capital P is the principal. This is our initial amount of money we begin with. The R is the annual interest rate. Okay, and even though it oftentimes is written as a percent, when we plug it into the equation here, it must be written as a decimal. The last number, N, is the number of times interest is compounded annually. Some accounts pay monthly, right? They compound the interest monthly. Some accounts may do it daily, some semi-annually. So it's important to read carefully to know what the value of N is. But it is measured in times per year. That's why it says annually. So if they do say that the number of times it's compounded is annually, N is 1. If they say something like, quarterly, it'd be 4, monthly would be 12, daily would be 365, and so on. So you got to pay close attention, to what that's described as. Now, the reason that's important is R is the annual interest rate. And so what you got to realize is you take the entire annual interest rate and divide it out among those many, times it's compounded. That's why we divide by N. Also, because t is always measured in years, right, this last part, we always have to multiply it by n, because for every year, n is the number of times this calculation actually happens. Now, it should be said, however, that this is very simple interest. An amount of money is placed into an account, and it's just simply left to grow over time. The more realistic scenario in many investments is that not only do you have an amount of money to start with that you let grow over time, but you also add to it. This equation right here does not model that, because to add money to it and have it grow over time, honestly, is a little more complicated, but it's a little more realistic. But just for the purposes of some basic modeling and understanding, we're going to go with this simple interest model. So in our first example, let's find the balance in an account that we let sit for 4 years. Okay, so we're going to start with $8,600, and that account is going to pay us 1.32% annual interest compounded quarterly. Okay, so what we want to take away from this is when it says compounded quarterly, that tells us right here that N equals 4, because that means it's done 4 times per year. So this right here, right, this annual interest rate, that means it's going to be our R. But remember, even though it's expressed as 1.32%, we have to write as a decimal. So to go from a percent, like 1.32% to a decimal, all you do is move the decimal place over 2 places. So this becomes 0.0132. Okay, so you may see this as a decimal, but it's actually a decimal percent. The entire thing has to be its own decimal, no percent. So move that decimal place over 2 places, okay? T is obviously our 4, right, because the number of years, and our P is, here going to be $8,600. Looking at what we're given, we have the big P, we have the R, the N, and the T. So obviously when it says find the balance, A is what our calculation is going to be looking at. So to set this thing up, we'll begin with A equals, and of course our P, our principal, is that $8,600. And then we, of course, have 1 plus our decimal, so 0.0132, divided by our R value, 4. And that's going to be raised up to 4 times per year, and we're going to let this sit here for 4 years. Now, when you calculate this, obviously it's not going to be a nice number, right? All this punching up and so on, simplifying is going to give you a decimal. But we want to round it to 2 places because it does represent money. So when you punch this in your calculator and simplify it up, you're going to get $9,065, and when we round 2 places, it's and 49 cents. Let's try another example, but this time let's let $9,000 sit in an account for 3 years in an account paying 1.46% annual interest. But this time it's going to be compounded monthly, which is common in many investments. So in this case, to find our amount, we'll start with our principal, $9,000. Okay, as a decimal here, remember 1.46% is 0.0146. So that number is going to be in this numerator. And because we're doing it monthly, that's obviously 12 times a year. So that will be our denominator. So it's going to be 12 times 3 years. So the exponent's really 36, which makes sense because if you do it monthly for 3 years, this calculation is made 36 times. Now again, we're going to go ahead and round this to 2 places, and when we type this in our calculator, we get $9,402.71. Now the last one I want to talk about is a special case, and we have to have a different formula for it because this is interest that's compounded continuously. What it means is that, going back to our original expression, the n, right, instead of being quarterly at 4 or monthly at 12 or even daily at 365, what if n was like infinity? That we were constantly, or in this case continuously is the way they worded, continuously compounding the interest. Well, what happens is the n's and this part of the equation, right, it all eventually becomes that value e. Okay, and that's where that special irrational number we talked about in the first part of the section comes into play. So when we come down to compound interest, right, that's done continuously, we don't have a value for n because it's infinity. And since n's not a number, we have to ask ourselves, what's happening to that equation when n becomes infinitely big? Well, it becomes the value e. And all of that can be simplified to be this, okay? So while this right here is the equation we're going to use for all compound interest, for all values of n, when n becomes infinitely big, we will use this because e is the value that part of the equation takes on when that happens. So every other letter stands for the same thing. A, of course, is still the amount in the account. P is the initial amount, the principal. And R and T still are the rate as a decimal and the time in years. Now, you may be thinking to yourself, if we're doing this, calculation all the time, continuously, nonstop, basically like an infinite number of times, wouldn't that grow the account so much more, more quickly? Well, yes, but no, because while we do a lot more calculations, each calculation still is infinitesimally small because, you're only having a little bit of growth every time. So while it is growing, and it may grow a little bit faster, right, than maybe even doing it daily or, whatever, it's still not going to be dramatic. So please don't think when we type this up, we're going to get these crazy big numbers and have incredibly fast growth. It's not the case. However, it does grow a little bit faster, okay? So when we set this up, for our first example, we're looking at $4,000. Okay, it's going to be 6% annual interest right away in this one. That right there is probably the reason we're going to get a much bigger number in this example, because in our previous examples, it was like, 1 point something percent. 6% is pretty good, right? So the real reason I think on this example we'll have a bigger number isn't so much the fact that it's E, but more that we have 6% interest. Also, we're going to let the balance sit for 5 years, okay? So let's go ahead and set that up. So we're going to look for the account amount, right, starting with $4,000 times E. And again, because this is 6% as a decimal, that's 0.06. So the exponent's going to be 0.06. And then we're going to let T be 5 years. Okay, and again, we're going to round this to 2 places just because we're looking for, modeling money. So the amount of money we're going to be left in this case is it's going to grow all the way to $5,399.44.